Welcome once again to another time value of money video. Now we're going to solve problem number 4 another way. And circled in red here is the problem again. Real quick, at date 0, you deposit $4 million into a bank, pays 1% interest a month. You withdraw $50,000 each month beginning at date 1. You deposited that $4 million at date 0, by the way. At what date will you first be unable to withdraw $50,000 from the account due to insufficient funds? So the cash flow date line was like this. At date 0, put in $4 million. At date 1, take out $50,000. Date 2, date 3, take out all the way to this unknown date end where we take out $50,000. I talked about that in the last video. Let's solve this problem a different way now. Okay? Solve this problem a different way. In this case, we're going to start like this. We're going to say, hey, at date 0, I've got $4 million in my account, and I'm just going to pretend for a second that that will earn interest at a rate of 1% a month for n months. Now, this is not what's going to happen, but we're going to start this way and then adjust to reality. So $4 million earning 1% a month for n months, and that would be the balance in our account. Now we're going to adjust it for reality. Minus the $50,000 withdrawal at date 1, which will therefore not earn interest at a rate of 1% for n minus 1 months. Okay? Again, remember cash flow date line, I'll just put it up here. Date 0 is plus 4 million, and date 1 minus 50K. Date 2 minus 50K, date 3 minus 50K, all the way to this unknown date n. We pretend it's an integer. Last time we can take out 50K. I'll circle that in a lovely purple color. That's the cash flow date line. Okay. So this 50,000 here was adjusting for this 50,000 here that wasn't going to earn interest. The $4 million here, we assume it all earns interest at 1% a month for n months. But when we take out this 50,000 right here and show it there, that will not earn interest at a rate of 1% for n minus 1 month. It will earn interest at 1% a month for 1 month. That's why this is n minus 1, and we got the big old minus sign there. That's what's important to see. All right. Now, what about this? Well, minus 50,000. And that will not earn interest at 1% a month for n minus 2 months. It will earn interest for 2 months. What about this one? Well, minus 50,000. Times 1.01 to n minus 3 power. This 50,000 right here will not earn interest at a rate of 1% a month for n minus 3 months. It will earn interest for 3 months at 1% a month. Okay? And then we go out here, minus, oops, that's okay, keep it in red, dot, 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 minus, and then here we have this last one, minus 50,000. That will not earn interest at a rate of 1% for n minus n months. And of course that's 0. Okay? And then all of this has to equal what? Well, it has to equal 0. Oh, that's an interesting way of looking at it. It's kind of realistic. 4 million, pretending it earns interest at 1% a month for n months, and then adjusting for the reality of the circumstance. Here, and here, and here, and everything in here, and then here. And that's got to equal 0. Okay, and we're pretending n is an integer. We know it's almost impossible for it to be an integer, highly unlikely, but it's okay to model it like this. So that's what we're doing. Now, here's something really neat. Watch this. Here I've got everything on the left-hand side of the equation, of course. So I'm now going to put just the 4 million times 1.01 to the nth power on the left-hand side. And I'm now going to take the 50,000 and move them to the other side as equal sign over, I guess, over here somewhere. And so they become positive. But I'm also going to do some factoring. So I'm going to there's one term common in this area right here. There's one term that's common to all those terms, and it's 50,000. So I'm going to factor out of 50,000, and then I'm going to put in the square brackets the terms that were multiplied by the 50,000s. And here we have 1.01 to the n minus 1, and here we have 1.01 to the n minus 2. And of course, I'm adding these now because we're on the other side of the equal sign. And then here we have I should probably say here, plus 1.01 to the n minus 3. And then plus dot 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 plus. And then the last term will be 1.01 to the n minus n, which is 0. And now I have this neat equation. Look at this equation here. Oops, what did I do? There we go. There's our equation. Let me circle that in lovely yellow. Very interesting equation. So let's solve this now. Let's solve this equation. Well, here's the first thing I do. I make use of my knowledge of interest factors. And in an earlier video, I had discussed in great detail the future value interest factor for an annuity. And what I observe right now is that value in the square brackets is really the sum for I equals 1 to n of 1 plus r to the power I minus 1. And if you remember back in that video where I was explaining the future value interest factor for an annuity in great detail, that's what this is. This is the FVIFA formula. We can't work with all those plus dot 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 pluses, as you'll recall. But we can work, and by the way, before I forget, if you try to plug in the value for 1 and then 2 all the way to n for this, you'll be building the value inside these square brackets, but starting here and then kind of going to this term, and so on, kind of backwards, but it's still the same sum. And so, again, what I want to say is this is the FVIFA, and in this case, R up there is 0.01, R equals 0.01, and N equals, well, unknown. That's what we're going to solve for. Oh yeah, it's starting to make sense now, I hope, for you. So let's now take advantage of our knowledge of future value interest factor for an annuity formulas. Okay. So here we have 4 million times 1.01 to the nth power. And now that equals 50,000 times FVIFA, R equals 0.01, N equals question mark. All right, let's solve. 4 million times 1.01 to the nth power equals 50,000 times 1.01 to the nth power minus 1 over 0.01. That is the FVIFA formula. Okay? And now what I'm going to do is I'm going to divide both sides by 50,000 and multiply both sides by 0.01. Okay? And in doing that, I'll get rid of this and I'll get rid of this. So 4 million divided by 50,000 is 80. 80 times 0.01 is 0.8. So we've got 0.8 times 1.01 to the nth power equals 1.01 to the nth power minus 1. Now we're in business. Now it's just a matter of algebra. So next we will, let's bring all the 1.01 to the n terms to the left-hand side, which means I'm going to subtract 1.01n from both sides. Then I'll get rid of it here and bring it over here. So I'm going to have 0.8 times 1.01 to the nth power minus 1.01 to the nth power equals minus 1. Okay? And I'll factor out the 1.01 to the nth power. And then I've got 0.8 minus 1 equals, multiplied by 1.01 to the nth equals minus 1. Okay? That leaves me with minus 0.2 times 1.01 to the nth equaling minus 1. I'll multiply both sides by plus 1, by minus 1, then I get rid of these minus signs. And now what? Well, the variable that we're solving for appears as an exponent. So once again, we'll make use of natural logs, but I guess first, probably the smartest thing to do first would be to divide both sides by 0.2. So we'll have 1.01 to the nth power equals 5. And now we'll take advantage of the natural log. So now what I'm going to say, I'll just do this in green. I'm going to say that the natural log of this equals the natural log of that. As long as you do the same thing to both sides of the equation, the equality still holds. And now we know the natural log of 1.01 to the nth power is equal to n times the natural log of 1.01. And over here on the right-hand side, we have the natural log of 5. And now I divide both sides by the natural log of 1.01, and we see that n equals the natural log of 5 divided by the natural log of 1.01. And when you do that, we see that n, of course, equals 161.747, which is the same answer we got in the video that preceded this. I just wanted to show you this different way of doing it. And, of course, it's a matter of interpretation. Once again, the 161st time that we withdraw 50,000, the check will go through, but it will not go through on our 162nd attempt. So the answer to the question is date 162. And that's all for this video. Thanks for watching.